This is Robin Scheibler with the speech team at Line Corporation, and today I will talk to you about unsupervised separation of speech for smooth communications. So first, I just want to say a few words about myself. So I was born in 1984 in Switzerland, where I lived for about 20 years, and during that time I went to EPFL in Lausanne, Switzerland to study signal processing. So then I did some exchange in Stockholm, and I worked in Zurich and Tokyo. And also I was part of the SafeCast citizen science movement to measure radiation after March 2011 in Japan. And after 2012, I went back to Switzerland to do my PhD at EPFL until 2017, when I moved to Tokyo Metropolitan University for a postdoc, and I stayed there until February 2020 this year. And in March 2020, I joined the Line in the speech team. So now I will go into the presentation. So the agenda is as follows. So first I will describe, what is source separation so that we really understand the problem. Then I will explain how do we recognize speech, because this is very important to be able to separate speech. And then I will go into the details of the algorithm. And finally, I will explain how we can make this algorithm going faster, which is my work at Line. So first, what is source separation? And I want to describe the cocktail party effect. So the cocktail party effect is when you are maybe in a crowded bar and there are lots of people around and everyone is having conversations simultaneously. And you have no problem focusing only on the person who is talking to you. And also you can decide to switch focus, and rather than the person that is in front of you, you may listen to the person who is behind you, and your brain is switching without problem. And this is known as the cocktail party effect. And one very important point to achieve this effect for the brain is that we have two ears. And this is the same for this dog here in the picture. And in that case, we have maybe two persons talking. So there's the man on the right and there's a woman on the left. So when the man talks, the sound will propagate from his mouth to the ears of the dog. And first, the sound will reach the right ear of the dog, and then after a small delay, it will reach the left ear of the dog. And also the loudness will be a little bit higher in the ear that is closest to the man. Now for the woman who is on the left, this is just the reverse, and the sound will reach first the left ear and then the right ear. And also the left ear will sound louder than in the right ear. So the brain is really good at picking up these cues and uses this to be able to focus on only one of the speech sources. So we can imagine to do the same, but just using microphones instead of ears. And here I just described the general system, and on the left we have sort of the environment. So there are two sources and they are mixed together to the propagation of a sound in space. However, this is hidden, so we don't have access to this, and all we have, so the input for us is the signal from the microphones. So and each of these signal is a slightly different mixture of the two persons talking. Then we have our algorithm, which will allow us to separate these sources, and at the output we want to have the separated sources. So now let's listen to maybe the input and the outputs of the algorithm. So first, here is the mixture at the microphone.
We were very close together in that moment. The men stared into each other's face.
To the smash.
So we can hear a man and a woman talking simultaneously. So at the output, this is what we expect. So first, the woman.
We were very close together in that moment. The men stared into each other's face.
And then the men.
So Huey and I did the managing ourselves, but it contributed to the smash.
So we can hear that we managed to separate these sources. So the second source we can hear faintly in the background, but it's much attenuated so that we can listen easily to each source individually. Now, before going into more details, I want to explain why this is useful in practical applications. So first, many of us nowadays have smart voice assistants in our home, and we can use them, we can ask them questions, or we can ask them to remind us about some tasks that we have to do, some events in our calendars, or we keep track of time when we're cooking. And however, our homes are fairly noisy places, so we may have children that are running and playing around, or there may be other people who are talking at the same time, or maybe the radio is playing or we're listening to music. But still, we expect the voice assistant to correctly understand us and respond to our requests. So using source separation, we may separate the voice from the different people in the scene and then correctly answer the request. So the second application we consider is automatic minutes taking. So during meetings, there are several people talking about different things. And we would like to keep track of what everyone has said, what was the content of the conversation, and what actions items were decided during the meeting. So normally, one of the participants in the meeting will do this and take notes, either by hand or with a computer, and then compile all of this after the meeting. However, this is using the brain power of one of the participants, and we rather offset this task to a machine. So we can imagine we place a voice recorder at the middle of the table, and we record the whole meeting. Now then, using sound source separation, we may separate the voice from the different participants in the meeting and compile what everyone has said. We can feed this to automatic speech recognition to transcribe this into text, and then we can do maybe keyword spotting keyword spotting to keep track of the main themes or maybe what actions were decided. Then another application may be in augmented hearing. So now that we're spending lots of time in Zoom meetings or maybe in virtual reality games, and we want to match the acoustic of the game or the meeting to common content for everyone. And we maybe have several people that are playing at the same time the game or participating in the meeting. So we may have to separate the voices to apply different effects on everyone separately. Now, another thing is the multiple sound event detection. And in this case, we don't aim only at recognizing voice, but also what other sounds are present in the scene. And here, an application may be that you are in a busy railway station, for example, Shinjuku Station, and you're placing a call to a restaurant to change a reservation, but it's very noisy. So you want to apply some algorithm for enhancement. So using sound source separation, you may separate the voice from the person talking from other sounds present in the scene. Then you may recognize from these other sounds that you are indeed in a railway station, and use this information to apply specific algorithms that are tailored for this acoustic environment. So now that I have described some applications, I want to describe how do we need the separation, so what characteristics we want for the separation. So first, we want the separation to be fast and light in computations because it will run on very small devices like edge terminals or maybe mobile phones. So these devices are battery powered, and we don't want to waste too many computations or battery power to do this. Then we want this to be very hands-off so that we don't have to update all the algorithms whenever we change the mobile phone or whenever we change the acoustic environments. So this is where having an unsupervised model is very useful because the same algorithm may run on every device. So finally, we want the output to be very high quality because the output from the algorithm will be fed to automatic speech recognition or maybe listened to by a human. And humans are very picky when it comes to noise and distortion. So now that I have described all this, I will explain how we recognize speech in order to separate it. So first, here is the spectrogram of a speech sample. So this is a kind of visual representation of sound, and the horizontal axis is time, so that the speech starts on the left and ends on the right of this image. Then the vertical axis describes the frequency content, so that the bottom part of the image is the low frequencies, and the top part of the image is the high frequencies. Then the color shows the loudness. So the blue parts are more the quiet parts in the speech, and the yellowish, greenish parts are the louder parts in the speech. So here we can observe some of the characteristics of speech. So the speech happens in short segments that are separated by quiet pauses. So this is because we speak in short bursts, so we say a few words, then we take a small pause and then continue to speak. However, on the frequency, we see that once we start speaking, sort of all the frequencies light up more or less at the same time. So this is kind of a general features of speech that we will use for the separation. Then we also want to be able, whether we have correctly separated the sources or not. So whether we still have a few sources mixed together or if this is only one source. So here, this is the pink line is sort of the loudness of the speech over time. And this is for just one source. So we see exactly what I have just described, which is the speech happens in short bursts. So then we have very quiet spaces, and then we have, again, some louder segments. Now, what happens if we add a second source? Then the pauses sort of fill up a little bit with sound. We still have some very big segments and some very quiet segments. And we can continue to add more sources. And we see that sort of the intensity over time or the loudness over time is more and more uniform. So this is for 4 and then 8 sources. And as we keep doing this, it looks more and more like just noise. So when we add more speakers, basically things sound more like noise. So we use this element to build a sort of spectrogram model for speech. So here on top is the speech segment, and then on the bottom, it is just the spectrogram, and we have stretched the power at one time over all the frequencies, so that we have these small pauses, and then all the frequencies light up at the same time. So still we have some very quiet segment and some very loud segments. And this is this kind of mixture that is a robust model for speech. So now that I have described all this, I will go into the separation algorithm itself. But before this, I will explain why this is a hard problem. So as in my previous slides, here we see on the left sort of the model of how speech mixes, and then the mixed microphone signals. However, then we apply the algorithm and get the separated sources at the output. But all this left part is completely unknown. So this means that we cannot really properly separate which effects are coming from the sources themselves, from the voice content, and which is coming from the environment, from the spatial propagation of sound. So to give an analogy, this is a little bit like trying to solve this equation, x plus y equal 11. So one solution to this equation may be x equal 2 and y equal 9, and then the result is 11, which is correct. But there is another solution, which is 7 plus 4, which also gives 11. And there are actually an infinite number of solutions. So we need to pick the right solution. It may not be just any solution. And in fact, the best solution is the solution that sounds the more like voice. And this is why we need to be able to recognize speech and voice sounds. So now I will describe the algorithm itself. So we start from the mixture signals from the microphone. We will first start from some guess of what the separation system should be like, which is guess 1 here. And then we obtain one first estimate of the separated sources. And as we see here, maybe the sources are not completely demixed at this point. So this is when we used a speech likeness test, sort of. So we say, okay, does this sound like speech or not? And for this, we use the spectrogram model that I just described. So are there lots of pauses and lots of loud components? Do all the frequencies sort of rise at the same time or not? And then based on this, we will decide of what to do next in the algorithm. So maybe it doesn't quite look like speech yet. So okay, we will update our guess to a second guess, guess number 2. And hopefully this guess will be better than the first one. And then we obtain a second estimation for the sources. And we will again do the test. Does it sound like speech or not? And in this case, it's a simple example. So maybe yes. And then if it does sound like speech, we will stop the algorithm. So in practice, we need to do this iteration a few more times. Also in practice, we need a way to do this sort of mathematically. So we will consider a function, which is here this blue line. And when this function is big, means that things are still very, very mixed together. So we don't have a clear separation of the sources. And when the function is small, then it means that the sources are well separated and sound indeed like speech. So what we want to find is the best place. So the place where this function is the smallest, where the sources are the most like speech. However, all we have access to is one initial guess. So this guess here is x0, and we want to go to the minimum, so the point that is indicated by the pink arrow. But we don't know the function, so visually we can tell, oh, this is the minimum. But in practice, all we can know is this x0, and then maybe the slope of the function, whether it's steep or shallow. So the way to do this is just like skiing. So we will look for where the slope is the steepest, and then go down. And this way, we're quite sure that we can go to the bottom of the slopes the fastest. So once we take a few steps, or we slide for a little bit, then we look again, okay, where is the slope the steepest? So maybe if it's the steepest on the right, we go to the right and continue. So the algorithm for this is called gradient descent. So here we have our guess, x0, and then we look at the slope, and this is this yellow arrow that points to the top of the mountain. So because we know where the top is, we can just go in the opposite direction. So we take a step in the opposite direction and get a second guess, x1. Now from this second guess, x1, we do the same thing. We say, oh, where is the top of the mountain? And then we go in the opposite direction. We take a second step. And we repeat this. And at some point, we get to the bottom. So this was very nice. So we got to the bottom. However, we have to decide, how long we go in each step. And if we go too fast, then things may go wrong. And I will show just such an example now. So now, because we want to go faster than before, we will take longer steps. So here is the first step. And we see that indeed, we went lower than in the first trial. And then we take a second step. But then, oh, oops, we missed the minimum by a little. And then if we take a third step, we go backward and we go up a little bit. So in this case, the algorithm fails. It goes up. It doesn't go down anymore. So what we want to have is another algorithm that is safer to use. And the algorithm that we use is called Majorization-Minimization. And the image that you may have is that of this dog here. So this Shiba dog here may run around freely, but has a leash, so that the dog cannot run away or go too far. So we will put a leash on our algorithm so that it doesn't go down too fast. And the way we do it in practice is that, again, we start from this point x0. And instead of the main function that is in blue, we will use this pink function. And this pink function should have a few properties. So one of them is that it touches the blue line exactly at x0. The second property is that it is always above the blue line. And then the third property is that it should be easier to minimize than the blue line. So here, because it is easier to minimize, we can find where it is the smallest directly, and we update our guess to where the pink function is the smallest. And starting from this second guess, we can find a second auxiliary function that is in pink here again. And we repeat this, so we find its minimum and find a new estimate. We repeat this. And as we go like this, we always go down. And because we know that the pink function is always above the blue line, there is no risk that we go too low. However, we see, okay, in the end, it is not so fast. So maybe it's nice, but maybe we want to go a little bit faster. So this is where we introduced recently new, faster separation algorithms at line. And unlike gradient descent, we cannot have just take a longer step or go a little bit further away. We need to find a new function that is tighter fitting than the first. So here, we have in pink, we have the same function that we had before. And then we have in yellow is a new function, a new auxiliary function. And it also touches the blue line at x0. And it is also always above the blue line. However, it is a little bit more fitting. And then when we take a step, it goes a little bit further away than it went for the pink line. And then we repeat this, and we see that, for example, here the second step is much better than before. And it allows us to go down much faster than before. And in summary, this is what we do in our new separation algorithm. So this is very nice. And we can quantify how much better the approach is. And here is a plot that has on the horizontal axis is the runtime of the algorithm in seconds. And then the vertical axis is like how good the separation is. So when the curve goes high, it means that the sources are very well separated. So if it goes up fast, it means it separates the sources very quickly. So these first 3 lines here, the blue, pink, and yellow lines, are the old algorithms. And now the green line here is for the new algorithm that we developed. And if we compare, for example, to go up to a certain point here that I indicate with a white arrow, it is 4 times faster to use our new algorithm than to use the previous best algorithm. Then we can listen to what the output sounds like. So here was an example with 5 sources mixed together.
I made no more overtures.
I
Three of them were Indians, also 3 other men.
And then we will listen to the previous algorithm. And it may be difficult to tell the difference, but in the middle of the segment, one of the sources is not well separated, and it is difficult to understand what the main speaker is saying. So please listen carefully.
I made no more overtures. With them were Indians, also 3 other men.
Now we can listen to the new algorithm. So it is given the same computation time, but may separate the sources better, so that in the middle of the segment, the speech is much clearer.
I made no more overtures. With them were Indians, also 3 other men.
Okay, and I just like to mention here that you can access the paper that describes this algorithm at the archive address on the bottom right. And we also shared the code for this algorithm on GitHub on the bottom left. Now to summarize, what do we want in source separation? So is we want to have fast algorithms, and we have shown faster algorithms than previous ones. We want the algorithms to be robust and also hands-off, that they may run on any device without being updated often. Then finally, we want to have a high output quality of the algorithms. And as a final thing, I want to mention that I developed a Python package for audio simulation. And in this package, there are some algorithms for blind source separation that are included. So if you would like to try out these algorithms yourself, you may check out this package. So thank you very much for your attention.